Hey guys, this is problem number 4 on the FO 2.12. Just want to show you how I might think about doing this problem. So we're asked to find any relative min, max, and then intervals of increasing, decreasing. So as always, we want to take the derivative because the derivative tells us information about the regular graph. But before that, I just want to show you this graph of y equals e to the x over here, because I think that's really important to helping us do this problem in the long run. As you can see, y equals e to the x is an exponential graph, as you can see. And what we do know about exponential graphs is that if it's not transformed by shifting it up or down, we know that there is actually a horizontal asymptote here, and in this case, there is never a time where the y value actually reaches 0, and so I just want to point that out, that that y never equals 0. Okay, so just want to remind you of that. We're going to need this information soon. Alright, so let's actually do this problem. Let's start by taking the derivative of f of x. So when we take the derivative, I look at this function and I go, hey, I see a product. So I see an f part here and a g part here. So what we know about the product rule is that we're going to have f times g prime plus f prime times g. And so when I actually do the product rule and take the derivatives of each part, I know that f is just x minus 2 itself. And the derivative of e to the x is e to the x, plus the derivative of x minus 2 is just, let's see, the derivative of x is 1, and the derivative of minus 2 is 0, so I'm just going to put 1, and then times g, which is just e to the x. Okay, so there's that. I'm going to clean this up a little bit. Let's see, I have x minus 2 times e to the x right here, and I know that I can use the distributive property and say this is just x e to the x minus 2 e to the x, and then plus, here's 1 times e to the x is just e to the x. There's some like terms there. Let's combine those. So I have x e to the x minus e to the x, because negative 2 and 1 gives me negative 1. Alright, so there's that, and then I'm just going to clean up a little bit more and turn it into the factored form. I know that they both have e to the x in common, so if I factor them, I know I'm going to have left an x minus 1. Cool, now what we're doing is we found the derivative, and now I want to find the critical numbers. And we know that critical numbers are the x value when the derivative equals 0 and when the derivative does not exist. In this case, only the derivative equals 0 matters because there are no times where it doesn't exist. So let's talk about when the derivative is equal to 0. So all I do is I'll set my derivative equal to 0, and my derivative is actually e to the x minus 1, and I try solving it. What's nice is that it's already in factored form, so I know that I can separate the two factors and say, okay, then e to the x equals 0, or x minus 1, the other factor, equals 0. Now, I'll do the right one, x minus 1 equals 0. I already know that's going to be x equals 1 for sure. That is a critical number. But let's look at e to the x equals 0. Now, before we even started this problem, remember how I mentioned up above here that e to the x can never equal 0. So this part, e to the x equals 0, doesn't actually give us any critical numbers. So the only critical numbers we got is x equals 1, or just one critical number. Alright, so that's nice. So I'm going to make a little table, or a little, actually a visual, where this is my critical number, x equals 1. And then I want to find out for my derivative what happens before and after. So let's see what if it's positive or negative before and after. So we can do a derivative test. Points. So what's a number that's less than 1? That's a really nice number. Probably 0. So I'm going to plug x equals 0 as a test into where should I plug it in? I have two functions. I got f of x and I have f prime of x. Which one do you think is the better option? Well, when we're doing the derivative test, we want to plug it into the derivative because the derivative tells us about the slope, which is what we really care about. So when I plug it into the derivative, f prime of 0 is equal to e to the 0 times 0 minus 1. And what is that? I know that e to the 0 is 1, because anything to the 0 power is 1, times 0 minus 1 is negative 1, which is just negative 1. So I know that all intervals before 1 is going to be negative. These are negative numbers. Okay, so let's test another one. X is equal to, what's after 1? The right side of 1, a number we can choose is maybe like 2. So I can do f prime of 2 is equal to e to the 2 times 2 minus 1, which is just equal to e to the 2 times 1, and we know that this is a positive number, which is greater than 0. So I'm going to put positive here. Now, just to remind ourselves, whenever the derivative is negative or positive, that tells us when the function is decreasing or increasing. Because if the slope is negative here, then that means if the slope is negative, it's going down or the function is decreasing. And if the slope is positive, we know that the function is increasing. So that begs us to ask the question, what is important about this critical number? Is it a min, a relative minimum? Is it a relative max, or is it neither? And the answer is, well, I always ask you why. What's the reason? So if we were kind of to draw a little sketch of what the function might look like, so here's my sketch, then we know that here's 1. I know that before 1, the function is decreasing, so it's probably going down. At 1, we know that the derivative was 0, so that means there's a flat point. And then after, it's increasing, so it's going up. So what does that make this critical number right here? That makes this a relative min. Okay? Okay, so now we have all the information we need right in this area. So using that information, we can say that the function, it has a relative min when x is equal to 1. We know that the relative max, there's none. We know that the function is increasing with all values that are greater than 1. So you can either write x is greater than 1, or the way I like to write it is, what are the left and right points? We know it's 1 to positive infinity. And we know it's decreasing when x is less than 1, or we write it in this way, negative infinity is a left bound, and it stops at 1. And there you go. This is the answer to the problem. And I have a graph for you here that shows you what it might look like, the actual values. So here it is up here. I moved it a little bit closer. All right, so let's take a look. So let's see if the relative min is x equals 1, and we see, yep, there is a relative min. Is there a max? There is no max, so that's correct. It's increasing when x is greater than 1. Yep, at this point, all these values are going up as the x increases, so these are increasing, which is correct. And we know that it's decreasing when x is less than 1. And that's right. As we go this way, we know that the graph goes down this whole time until it reaches 1. Ooh, that's bad. Going down. Okay, so we know that this whole section is decreasing. We know that this whole section is increasing. And I guess I should say this is going to infinity, so there you go, guys.